Anyway, so today I'm going to tell you about some things that I've been doing, but I'm going to present, most of the work that I'm going to present has been done by my actual postdoc, Anna Niemiec, and my student, Sutieng Tam, who is defending her PhD at the end of this month. And basically, I'm going to center my talk around what I call cosmic beasts, so the most massive galaxy clusters. So I'm going to start by introducing the main tool that I'm using, which is gravitational lensing. So for the people that know me, you know that I've been doing that for many years now. And talk about observations, what we need to do the analysis that I'm going to present. And then present some of the things that you can do with those objects, like in a pretty broad vision. And then I'll conclude and give you some hints on what's happening next. So to start with, this is a screenshot from the Millennium 2 simulation that you might have seen before. So what you can see is the distribution of dark matter over really large scales. So the matter is accreted along those filaments. And today in my talk, I'm going to concentrate on the intersection of those filaments, which are hosting those really massive galaxy clusters that I call cosmic beasts, and that are also called nodes of the cosmic web. So like I said, I'm using the main tool I'm using, and I insist this is a tool. This is not anything more than this, is gravitational lensing. So if you look at the image on the left, you can see an optical bench where the observer is here. You have a galaxy that is emitting a source. If there is nothing between us and this galaxy, then you're going to see this galaxy intrinsically fainter and fainter as it's further and further away from us. However, if you end up putting something in between this galaxy and us, then the light rays are going to be distorted, magnified, and in that sense, being lensed. If you look at the picture that you can see on the right-hand side of the slide, it's Einstein and Eddington sitting on a bench in Cambridge in 1919, sorry. And the reason why I'm putting this picture here is because lensing was predicted by GR based on the assumption that an inputted mass density is going to locally deform the space-time. And it's purely geometrical, has no dependence with the photon energy, but this was just a hypothesis back then. And Eddington in 1919 was actually the first one to confirm, first of all, the lensing hypothesis, and that was also the first observational confirmation of GR. So here is a quick history reminder. How did he do that? So what happened is that on the 29th of May, 1919, there was a total solar eclipse happening in front of a really bright constellation of stars. And that was visible from, if you look at the image on the left, from Brazil and Africa. So what Eddington did is that in January and February, he measured the true position of the stars from Oxford, and then sent two teams, one in Brazil and one in Principe, a small island on the western coast of Africa. He was part of the African trip to ensure against bad weather and ensure to have like good measurements. So during the totality of the eclipse, they measured the new position of the stars in the constellation. Both teams were lucky enough that they both got measurements. In November 1919, he published his results. So as much as Newtonian gravity is also predicting an offset in position between with such an event, the offset measured by Eddington was agreeing with the one predicted by GR and non-Newtonian gravity. So like I said, that was the first observational confirmation of GR actually. So we go back to our optical bench, and now you have a small equation put on my slide, and that is alpha. Alpha is, so if you have your lens, like I said, your light rays are going to be distorted and deviated and even magnified in some cases. And so your source is going to appear at an angular position in the lens plane alpha. And so this alpha is equal to a cosmological distance ratio, which is the distance between the lens and the source, and us and the source, times the gravitational potential of the lens. And what is interesting and important here is that this gravitational potential is directly proportional to the total mass of your lens. So if you believe in dark matter, for example, and I kind of do, so I'm going to assume that dark matter exists all along this talk. This is an excellent and one of the most efficient tools to actually understand and trace dark matter. Because, like I said earlier, there is no dependence with photon energy. So here, today, the lens is going to be a galaxy cluster. And so those are the most massive observable structures. And in a cluster, you're going to observe mainly two lensing regimes. So if you look at the small animation that I have here, you can see in the center of the cluster when it's the reddest, so this is the density in pinkish, distortions are going to be large. You're going to observe gravitational arcs, multiple images, like your wavefront is going to be broken by the gravitational potential of the lens, and you're going to be in the strong lensing regime. As you're going further and further away from the cluster core, you're going to enter the weak lensing regime, where distortions are going to be much, much smaller. And in this case, it's not going to be visible on an image. You're going to need a statistical analysis of these deformations, but I'll present that in a few slides. So let's go back to history, because I kind of like this part of history, so I repeat myself during seminars. So gravitational lensing in clusters goes back to 1987. When the first giant arc was discovered in a well-known cluster, thanks to that, actually, Able 370. So on the left here, you can see the CFHT image on which the team worked. And you can see in the southern part, I'm sorry, you can't see my mouse, this extended feature that is a bit curved down to the bright galaxy. And in 1988, they published a spectroscopy of this feature and realized that actually this was a galaxy, an object that was behind the cluster. So the cluster is at 0.375 in redshift, and this object is at 0.725. So that was the first confirmation of cluster strong lensing. However, I insist by saying that they were extremely lucky. Because those objects, most of the lensing objects are extremely faint. They're usually not extended. And so to see them, you need really high resolution data. And this is extremely difficult to observe from the ground. And to give you an idea about that is exactly the same field observed with Hubble in 1996 by the camera with PIC 2. You can see clearly the extended arc that is seen in the CFHT image, but you can see also in the northern part some other arcs that are extremely faint and invisible on the CFHT image. So basically what I'm trying to say here is that without Hubble, it would have been almost impossible to do properly cluster lensing analysis. So what I said earlier is that the good thing with lensing is that the angular position of your lens image is going to be proportional to your gravitational potential, which is proportional to the total mass. So from there, what you can do is either you can try to study dark matter, like I said, because you can directly observe stars, you can directly observe the gas in a cluster. And so by a simple subtraction, you can get the dark matter distribution. Then if you also remember what I said, is that your light rays are magnified. This magnification will help you see extremely faint objects and distant objects that would not be seen in a blank field. So you can use that, your cluster, as a natural telescope in order to observe the high redshift universe, for example. But again, I'll give you a few examples of that later on. Another point is that it's also sensitive to the geometry of the universe. You can use lensing to constrain cosmological parameters thanks to the different lens object at different redshifts. So you can sample the redshift space behind a cluster. I'm not going to talk about that today, but I'm happy to answer any questions later on. So then we move on to weak lensing. So we're basically in the outskirts of clusters. And in theory, weak lensing is pretty simple because it's what we call the linear regime of lensing. And so basically in the weak lensing regime, only the ellipticity of your source is going to be distorted by your cluster. So basically the ellipticity you observe, so the ellipticity of the image, is equal to the ellipticity of the source, so the intrinsic ellipticity of the object, plus a lensing term, which is gamma over 1 minus kappa, gamma being the shear and kappa being the convergence. So basically what's going to happen if you look at the sketch below is that imagine your lens source is purely circular, you apply some lensing, the shear, the convergence is going to increase the size of your source, and the shear is going to reduce it in one direction and stretch it in the other. So from a purely circular galaxy, you lens it, you end up with an ellipse. So this is the theory, but in practice, it's not that easy, unfortunately, because you don't know the true ellipticity of your source. And so what we're going to do is that we're going to, if you look at this simulation here, so on the left-hand side, you can clearly see the core of the cluster in the left bottom corner, where the distortions are pretty large and obviously visible by eye. And if you look at the square in the corner, which has a zoom in on the right-hand side, this is the weak lensing regime. You look at the sources, and by eye like this, you can think that all your sources are distorted quite randomly. However, if you average over this region, you will see, if you can see the small, I'm losing my words. At the top right corner, I'm missing a word.
Alignment?
Yeah, thank you. You can see that there is a preferred alignment if you average over all of the sources. So if we go back to our initial equation, if you average over a sufficiently large number of galaxies, and that depends on your data, but we can talk about that later on, and you assume that on average, because you have a sufficient number of sources, the intrinsic ellipticity of your source is random, then this term goes to 0, and the ellipticity of your image is directly basically the lensing term. So this is basically how you do weak lensing. I'll finish my introduction by showing the sketch that you're going to see on most of my slides on the top right corner, because I'm going to chat about basically 3 different scales today. So the really inner core of the cluster, where you're going to observe strong lensing, up to the virial radius of the cluster, where you observe weak lensing, and then we're going to even go further, where you're going to start tracing the inflow of matter from the large-scale filaments, if you remember the Millennium 2 snapshot that I showed earlier. But like I said, lensing is just a tool, and with just lensing, you can't do much. So we will, as you'll see, you need to combine with multi-wavelength observations in order to have to draw conclusions. So now let's move on to what we need to do lensing, basically, lensing analysis. So this is the core of a cluster called HUBBLE 2744. And all the small circles that you can see on this image are actually lensed multiple images of sources that are behind the cluster. And even though, so it's not obvious that all of this circle are highlighting a source, because some of them are extremely faint. But because they're extremely faint, you can imagine that, like I said earlier, ground-based data are not allowing you to detect those. So basically, you need high-resolution data, and up to now, it's basically only HSC, so the Hubble that can provide us with that. But also, if you remember the angular position equal the cosmological distance ratio times the gravitational potential, you need to know the distance of those sources to us. So you need spectroscopic redshift. So to basically, if we concentrate on the strong lensing for now, the deep high resolution imaging have been provided by an observing campaign called the Hubble Frontier Fields. So I know that some of you have heard about that. So basically, it was those are the deepest observations of cluster cores that have ever been taken, but only on 6 clusters. And the idea behind the campaign was to go extremely deep on the cluster cores to use strong lensing. And those clusters that are extremely strong lenses in order to observe the high redshift universe. So use this magnification and this natural telescope effect that is provided by lensing. However, as much as you can study the high redshift universe, you can also detect so many strongly lensed objects that you can recover the mass of your clusters and in your cluster cores with extremely high precision. So while at HSC is giving you this extremely high resolution imaging and extremely deep, still you don't have distances to your lens sources. And another really amazing instrument that had its first light back in summer 2014 or winter 2014, depending on which hemisphere you're in, is MUSE on the DLT. So MUSE is an IFU. So basically it was a field of view of 1 by 1 square arc minute. And this is absolutely ideal because this is roughly the size of the core of a galaxy cluster at redshift 0.3, 0.5. And so here are examples of clusters that have been observed with MUSE. But basically, if you want to get an idea of what you're getting, is in the bottom right, you have a MUSE image of Able 2744. So the same cluster I showed you before, taken by HSC. And all the circles here are spectroscopic redshift measurements. So basically, because it's an IFU, you're getting a spectroscopic redshift for each object in your field. Obviously, depending on the observing time, but we can discuss this later on. So this is another example, recent work that I've been doing with a student at EPFL, Baptiste Klein. So we looked at MUSE imaging of 3 really massive galaxy clusters. You can see them here. I can give you the names, but it's just letter and numbers, so it means a lot to me. It might not to you. I just insist on the one on the left, MS0451, because I'm going to present Su Tieng's work on this cluster, and she's using these observations. So basically what we did in this analysis is that we use the HSC imaging plus the MUSE observations of those clusters to get extremely precise mass models, because we could confirm, first of all, multiplicity. So we have this object that have similar colors, that have similar morphology, but we don't have their distance. But thanks to spectroscopy, we can know that they're like all multiple images of the same background source. And so we end up with mass precision down to like a few percent. And we even, because that's the power of MUSE, we even could detect multiple images that are not even visible in the HSC image. So as an example, if you look in MS0451, on the right-hand side of the cluster image, you have R1 and R2, and those 2 images are invisible on the HSC image, as an example. Anyway, so we were concentrating basically on the strong lensing for now, but I cannot give a talk without talking about Buffalo, so I'm sorry for the acronym in advance, even though as one of the PI I should assume it, but I do not. So Buffalo is a large HSC program that we got awarded back in 2018. And if you remember what I was saying about the frontier fields, so the frontier fields is 6 clusters, and only the core was observed, but extremely deep. And so with Buffalo, what we asked for is a spatial extension around these cores in order to have high resolution data to do weak lensing, basically. So you can see the 6 fields with the 6 mosaic on the left-hand side. The idea behind Buffalo is not only the weak lensing, but also, again, looking at the high redshift universe and properly do cosmological tests, and you understand why in a few slides, because like this, you can combine strong and weak lensing and properly map the mass distribution in your cluster. So now let's talk about a bit of science. But before that, I mean, I'm not saying that mass modeling is not science, but it's a tool again. Says the mass modeler. So I'm allowed to say that. But anyway, so everything that I'm going to present now depends on mass models. So without reconstructing the mass distribution of your cluster, you can't do anything that I'm going to present after that. So basically, your mass modeling is extremely important. And well, depending on what you want to look at, you can concentrate on the core of clusters and so strong lensing only. But if you want to look at structure evolution, information, and so on, you're going to need to combine the strong and the weak lensing regime. And for that, this is not as trivial as it seems, because one is non-linear, the strong lensing, and another one is linear, the weak lensing. Anyway, in Buffalo, and that was exported from the Frontier Field campaign, is that we have a mass modeling challenge with all the clusters being modeled by basically almost all the teams that are doing lensing mass modeling in the community. And we deliver those mass models to the community, so they're being made public, so non-lensing experts basically can use those models to do the science they want to. You have 3 panels at the bottom of my slide. They're showing you basically mass contours on the left, so what you recover from your mass model. Then you have the density profiles, and then you have magnification maps, magnification that are extremely important if you want to recover the intrinsic properties of your lens sources that you observe in the cluster core. I'll highlight some work done by Anna because this is really important. She developed a new method called hybrid lens tool. Why hybrid? Because lens tool already existed and is the software that we've been using for years. However, lens tool was incapable of properly combining strong and weak lensing, but she did it. It's been 10 years that Eric Julot and myself have tried to do it, and she did it in a year and a half. So this is quite amazing. I was anyway. I am extremely happy about that. So basically, it's if you look at the left panel, what you can see is a simulated cluster mass distribution on the top row. Then basically what a hybrid lens tool is going to do is it's going to combine 2 different methods, which is a parametric method and a non-parametric method. I'm not going to enter the details. I'm happy to talk about that later on, but this can be quite boring if you're not doing mass modeling. But basically the middle panel is showing you what we used to do is we first model the strong lensing separately, then we have a best fit, and then we add the weak lensing for the wider field of view. So this is what you have, the recovery of this mass distribution with the sequential fit. And then on the right-hand side, you can see the joint fit, so the new method. So by eye, it's not absolutely crazily visible, the improvement. However, if you look on the right-hand side with the panel, you can see the density as a function of radius. and the input is in black, and the joint fit is in orange, and the sequential fit is in cyan. And what you can see is the sequential fit tended to overestimate the mass distribution, and the joint fit though is giving you a much more realistic recovery of the mass distribution. So basically, like the value I'm quoting in the slide is like with the joint fit, we're getting to up to 1.5 sigma from the true value compared to a few sigmas beforehand. Anyway, so once you have your mass model, and obviously you're going to use Hubble lens still because this is the best method ever. This is me being extremely objective. You can do many things. So I'm going to start by looking at the high redshift. Even though this is not my expertise, this is one of the main goals of all of those large programs with Hubble. So frontier fields, Buffalo, and relics also. Anyway, so you use this lens magnification in order to see really faint galaxies and so extremely high redshift galaxy. So with Buffalo, we reaching redshift 10. So to give you an idea, today Buffalo was designed to cover to overlap with the speedster coverage of the frontier fields clusters. And the idea was because Spitzer is the near infrared, so it gives you the age and the stellar mass, and HST will give you the what we call the photometric dropout. Is that a method to confirm that your galaxy is really high redshift and not more medium redshift, like less than 3 contaminant. So today we have around 25 galaxies at redshift 8 to 10. With Buffalo, we expect to add 10 to that. So 10 means maybe nothing to you, but this is basically almost half of what is already existing. So this is basically tripling the sample of extremely high galaxy, high redshift galaxy, and that will allow us to constrain reionization, basically. So here are examples of former detections. So redshift 11, redshift 9, and redshift 10 in some clusters. Now I'm going to move more to cluster physics because this is my my thing. One thing that I got to know and that I was not much aware of is actually intra-cluster light. And so if you look at this image on the left, you can see the stellar distribution in a cluster, which is a simulated cluster with obviously hydrodynamical simulation, CEGO. And the bottom panel, you can see the ICL. So what is the ICL? The ICL is made of the stars that are not gravitationally bound to galaxies. And so they're basically the result of galaxy interactions. And in some clusters, they can represent up to 40% of the stellar mass. So they're it is a non-negligible component. And in a recent paper, what they actually showed is that the ICL is also extremely well tracing the dark matter distribution, at least in cluster really inner cores. The problem with the ICL is that you need, first of all, you need HST data. You can't do ICL studies with non-space data because you need extremely high resolution. You need a data reduction that is extremely specific. So it's been really difficult for ICL people to study the ICL in the outskirts of clusters because HST time costs a lot of money, and so wide mosaic around clusters are not that common. So that's why it's quite a strong component of Buffalo, because with this mosaic that are extending further away from the cluster core, they can try to study the ICL and try to understand really what it comes from. And one hypothesis is that it might actually have different origins depending on the region of the cluster where you trace it. So It can be the shredding of the dwarf galaxies. It can be due to violent mergers or pre-processing of infalling structures, so like smaller clusters or groups, etc. But basically, there is a lot of work to do, and Buffalo data are really adapted to it. So now I'm going to talk about the cluster evolution, like related to basically most of what I've been talking about is like lensing, combination of strong and weak lensing in order to map the entire mass distribution of your cluster. So as much as it's interesting to know the mass distribution of your cluster, so what you see on the right-hand side is an HSE image of one of the frontier fields cluster, and the blue haze is the dark matter distribution. And so this is what you get from a strong plus weak lensing mass modeling. What I highlight in orange are the different substructures in the cluster. So the cluster core is actually, of this cluster, is actually made of two clusters that are about to merge. But this is the strong lensing region. And then you have two other circles, orange circles, that are showing you like much lower mass substructures. Those two substructures are like group scale, so a few 10 to the 13 solar mass. So from that, you can't do much if you want to look at, if you want to understand the history of your cluster. However, what you can try to do is to constrain dark matter particle nature. One way to do that is actually to count and weight the different substructures that I've been telling you about. And this is basically different dark matter type are gonna give you different observational signatures. And so this is a sketch that I've made, so don't take it extremely precisely, but that's to illustrate my words, is that depending on if your dark matter is cold or self-interacting or warm, for example, you're going to have more or less of those substructures that I'm telling you about and that you detect from your lensing analysis. So basically, dark matter is going to change the lumpiness of your galaxy cluster. Then you have other ways to look at probes of dark matter using just the pure mass distribution, is looking at the shape of your strong lensing region in clusters. But I'm happy to answer any questions about that, but I'll just move on to once you have your mass distribution, you can count and weight your substructures and compare that with predictions from numerical simulations using different type of dark matter and so on. But if you're more interested into the cluster evolution, so the growth of clusters and so on, your lensing is not going to be enough. I mean, your blue haze on your HSE image is beautiful for a press release, but that's basically it. You can't do much. So you're going to need to turn to multi-wavelength observations. One of the main ones that we're using is obviously the X-rays, because it gives you the hot gas distribution, the gas distribution in your cluster, and which is the second most important component in your cluster. And so what you're going to look at is the different gas light or stellar distribution peaks compared to the dark matter, and that can give you an insight on is your cluster merging, is your cluster not merging, is your cluster relaxed or not, and so on, so forth. It can also be actually a probe of dark matter nature, because different dark matter are predicting also different offsets, can predict offsets between your dark matter peak and your light or gas peak. But basically, you can end up by retracing the history of your cluster, as you can see here. So it's the same cluster, and this is the story of what happened to it, is that C1 is the main cluster, C2 is originating from the substructure detecting by weak lensing that we identified as being a large-scale filament aligned along the line of sight. And it's on its way to merge with C1 So it's just before the first core passage, basically. So this is a work that I've done 2 years ago, a year and a half ago. And this is a really massive cluster called 0717 that I also nicknamed my nightmare because I've been working on it since my PhD. And so what you can see here is basically the mass distribution of the cluster. So in blue are all the substructures that I detected using strong and weak lensing. And this is of a really large scale. Sorry, in orange. And in blue are the counterparts in the X-ray. And what it tells you is that this cluster is extremely massive. Good. It tells you that it has a lot of infalling substructures. Good. But again, it doesn't tell you much at the end of the day in terms of growth of structure. This is a cluster that is it's actually the most massive cluster that we know of at a redshift of greater than 0.5. So then you can suppose that it can be a really good test for the cosmological paradigm. And so what you can do, and that's what I did, is turn to numerical simulation to try to see if you can find those objects in numerical simulation. So we looked into CEAGLE, so hydrodynamical simulations, as well as MXXL, but I'm not going to present the MXXL results today. But basically, we found one cluster of the 24 that they have that had a similar mass. And we tried to identify the substructures, as you can see on the right-hand side. All the cyan circles are substructures of like similar mass range to what we had on the real mass distribution of 0717. And we looked at the infall of the substructures as a function of redshift. And we could estimate a growth rate. And we could also look at the gas fraction in those substructures, which is in excellent agreement with what we measure from observations, with an infall distance between redshift 0.5 and 0.3 of roughly 2 megaparsec. But if I'm getting there, it's to show you that this is only one cluster, but that one cluster is even, is the progenitor of, again, other massive clusters that we observe at lower redshift, like redshift 0.3. And you have an example on the plot on the right-hand side with HUBBLE 2744, which is at 0.3. And you can see the distribution, the density profile of the core in dash, the galaxy component in a dotted line, and of the substructures in a plain line. And what you can see is actually what we observe in terms of peak of substructure correspond to what is observed in the simulation. So such a cluster at 0.55 seems to be a progenitor of a similar cluster at 0.3, like HUBBLE 2744. HUBBLE 2744 was the subject of papers where it was a candidate for ruling out lambda CDM. And the message here is that basically, if you do a proper comparison between simulations and observations, you can, first of all, actually do a consistent test of cosmology, and that even if those clusters are at the limit of the lambda CDM paradigm, lambda CDM for now is still holding. I'll finish up by talking about the work from Su Tiang, so my student that I mentioned earlier on MS0451, that one cluster that I showed you earlier. And so the idea of her work was because with Buffalo now, we have 6 clusters with like relatively wide HST mosaic. Beforehand, only one cluster had a wide field HST mosaic, and that was MS0451. So 41 pointings of HST, providing unique weak lensing data with high precision weak lensing analysis. And so most of her, the start of her PhD was to work on this cluster and try to map the mass distribution, also because it's extremely massive. It's a merging cluster. In the core, you can see 2 clear components. It is also a cluster that could have been a really good candidate for possible large-scale filament detection. because we had hints from previous ground-based weak lensing analysis from Nicolas Martinet. So what you can see on the left is a pure, simple convergence map used done by using KS93, which is a simple inversion method with weak lensing data only. It has no optimization, nothing. And then a similar map, but done with lens tools, so an optimized method that combines strong and weak lensing. Here, the message that you need to take home is, and this is another work from Su Tiang, because she tested those two methods on the Bahamas set of simulations, and showed that depending on the science you want to do, the two methods are going to be extremely useful. However, if you concentrate on the detection of substructures and possibly filaments, you need to go for optimized versions, and you need to go for the combination of the lensing regimes. So quickly for the story of MS0451, what you can see here is the same convergence map, but where Su Tiang has subtracted the cluster core just to see the low mass substructures and what remains. And so you can see in that she detects a lot of substructures, but only a few are the cluster redshift. You can see them highlighted in red. They have masses of the group scale, so a few 10 to the 13 solar mass, so they're in falling objects, and that highlights the possibility of three preferred directions, so possible filament detections. If you look at the new image now, on the right-hand side, what you can see are actually in magenta, the contours from the ground-based weak lensing analysis from Nicolas Martinet back in 2016. And you can see that apart from the most massive, so if I go back and forth, so basically substructure number 2 is detected in the ground-based observation analysis, and substructure 4. Martinet et al. Discussed the possible detection of filaments, but this is basically kind of confirmed by Su Tiang's analysis. I'm not gonna go any further into the story of MS0451. The only thing that I'm gonna tell you is if you're taking into account the Buffalo set of data that we're getting now, is that such an analysis on 0451 is extremely helpful because it's an ideal test. It's an ideal set of data to compare to simulations. So now we have 6 more clusters to come, and we might be able to put a bit more stringent constraints on cluster evolution and hopefully dark matter's nature. Last but not least, really nice things that you can also do with lensing and frontier field / Buffalo type of data is you can actually detect really cool objects. So this is the first strongly lensed, multiply imaged supernova called nicknamed Residing. I'm happy to tell you more about that object because it's a fascinating one, and also one that demonstrated that our mass modeling techniques, and I include most of the teams doing lensing, cluster lensing in the community, are, yes, systematic limited, but not that bad, because we could predict the reappearance of one of the image of the supernova, and most of actually right. And still in the same galaxy as Residing, we could observe the first lens star at a redshift of 1.5, again strongly lensed and with a magnification factor predicted to be more than 10,000. And again, I'm happy to tell you more about it. I'll just quickly finish and conclude. Open collaboration. Our observations got completed in June this year. If you want to join, this is really easy. You send me an email or to Charles Steinhardt, the other PI of the collaboration. Or if you just want to know more, you can follow us on Twitter and Facebook, because this is how you do things nowadays. And yes, Remember, lensing is only a tool. Multi-wavelength, combination with multi-wavelength is the key. And cosmological tests are needed, but most of them can only be done with this multi-wavelength analysis. So basically, you need to turn to Hydra simulations. I'll finish by advertising the work of a few people. So Anna, that I've already mentioned, who started her postdoc in Durham on the 1st of May. She hasn't been to Durham yet, by the way, because of the lockdown, but she's being paid by Durham, so we say. We have so the overview paper of the program is out. It was published a month back. We're working on the first cluster, Able 370, that was fully observed. We have the first high redshift candidate catalog that has been distributed. Anna is finalizing the strong plus weak lensing analysis of Able 370, and with that, all the pipeline and the machinery, so we can run everything automatically on the other clusters. And the mass modeling challenge will provide the models for Able 370 by the end of this year. Guillaume Malher, who is also a postdoc at University of Michigan, is also joining Durham in November. David Lagatuta is also already in Durham, and Anna, who is not the other Anna Asebron, is not joining Durham, but I hope that I will get her to join Durham at some point. But anyway, all of these four are actually running most of the working groups. And so this is why their effort should be acknowledged. And I will leave you here. Thank you.